So the first form of proofs we're going to cover in this session is basically the direct proof, which is you have A implies B. So what you're going to do is you're going to try and get to B using A. And this is something we've done before, so this one is going to be relatively okay to handle. So again, the whole idea behind direct is you have A, gives you your B, and you're going to use A to get to B. Right, so let's go through examples of the proofs. So the first theorem you're going to tackle is if G is bipartite, then every cycle in G is of even length. So the first thing we need to look at, what is A and what is B? So A is G is bipartite, and B is every cycle of G is of even length. So we need to prove, the required to prove is that every cycle of G is of even length, given that G is bipartite. And let's just finish that. There we go. Okay, so one of the other things that you need to think about, particularly when you're proving, is what do you know about bipartite graphs? What do you know about cycles? Because the whole idea behind a proof is you're going to end up utilizing the definitions and theory that you already know to prove, what you want to actually prove, that every cycle of G is of even length if that G is bipartite. So let's first begin with basically how do we represent cycles? So how do we represent a cycle? So we can represent a cycle by basically writing it as a closed walk where you end up not having repeated vertices. So in regards to that, you could relabel your vertices so that it actually forms a situation of, if it was length P, let's just use a different color. Say your cycle was length P, you would have V1, V2, V3, all the way to Vp, and then back to V1 again. Because when you have a cycle, you don't repeat vertices, so you can number them very nicely, and you end at the same vertex that you began with. So your terminal and your initial vertices are the same. So we have a situation of how we can actually, represent an arbitrary cycle of, say, length P. Then we have a situation of, if we can find that P is even, an even number, we kind of sort it. So that gives us something to aim for. So we have a cycle Cp, by the way, and we represent it as V1 all the way to Vp. And again, we can relabel our vertices so that it is in that nice pretty order. Okay, so now we actually need to know something about bipartite graphs to maybe help us out. So what do we know about bipartite graphs? And what we know about bipartite graphs is that there are only edges between vertices from the different sets, the disjoint sets. So we're going to have to look at that kind of idea in that the vertices in the cycle are going to alternate between these sets. So let's just write that down. What do we know about bipartite graph? The edges are between vertices of the different sets. And that means when we look at our actual cycle, say if you have V1, V2 has to be in a different set, and then V3 has to be in the previous set. So that's going to give us something to work with in proving that it's an even cycle. So the idea again of theorems and proofs is if you're proving it directly, you're utilizing A to show that B is going to come out. So you're going to have an outcome of B. And then when you're thinking about it with the thought process, so you first write down what exactly are you required to prove. Then you also write down what do you know so far. And then you're going to try and connect the dots basically. So you know how to represent cycles. You know how to represent cycles of length P. You know that you're going to somehow try and get that P is equal to an even number. Then what do you know about bipartite graphs? You know that the edges are between the vertices of different sets. And that should slowly start getting you thinking about, well, if the edges are only between the vertices of different sets, and I have a cycle, that means that when I end up looking at, our cycle, the V1, the V3, etc. are going to be in the same set, whereas the V2s, the V4s, and so on are going to be in a different set. Then you're going to be like, oh, so can I prove that the VP, or can I show that that VP is going to be in the one set, and it's going to be in the set where all the numbers are represented by even numbers. So that's the idea process. So let's now begin this proof. So remember, your proof is also basically telling your reader what exactly is happening. So the first thing you're going to do is you're going to define that cycle. So you're going to say, let C be a cycle in G, and let C be such that you have B, and the dot dot is such that you have V1, V2, V3, and it continues on to VP to V1. Okay, what else do you know? Then, because it is a cycle, and a cycle is made up of paths, the vertices are going to be different. So you tell the reader that. You say, then V1, V2, V3 to VP are all different. Okay, so they're all different vertices, they're all different, and the cycle is of length P. And the length of C is P. So you utilize that one fact where you created an arbitrary cycle where you relabeled your vertices so that when you do your cycle, it's V1, V2, V3 all the way to VP and back to V1. Then you say, okay, because we know it's a cycle, the vertices aren't repeated. That means that V1 to VP are different, and that also indicates to us that the length of C is P, and that just comes from determining the length of a walk essentially, because remember, your path, closed path, is still a walk. Okay, next up you say G is bipartite. So all the vertices are partitioned into two sets, basically. They're either going to be of set, let's say S and set N. You can label those sets anything that you want. So you could have also said like odd and even, so sets VO and VE kind of a situation. So let's write that. G is bipartite. So the vertices can be partitioned into two sets. We're going to call them, say, VS and VN. Now what we're going to do is we're going to say that V1 is in set VS. Let V1 be an element of VS. Okay, but then we know that V1, V2 is an edge because it's in our cycle, right? So then, as V1, V2 is an edge, that means that V2 must be an element of the other set, the set Vn. And I just want to switch the sets around so it matches your notes. So let's just do this. So we're going to label this set N, and then V2 is going to be then, it'd be useful if my words would actually write on the screen. Okay, let's try this one more time. Then V2 is an element of VS. So the whole idea behind that is basically we're just saying if V1, V2 is an edge, then V1 must be of the one set and V2 must be of the other set. And you can follow this approach. So now you have V2, V3 is an edge. Okay, so as V2, V3 is an element of the edge, which set or is an edge, then V3 must be an element of the Vn. Because if V2, V3 is an edge, then and V2 is in Vs, then V3 must be in Vn. And you can basically repeat this, essentially, because it results in a pattern. Okay, so this results in a pattern. And now we have a situation where our Vn consists of odd numbers and our Vs consists of even numbers. So we have the vertices in Vn are odd numbered and the vertices in Vs are even numbered. Now we need to show that Vp is going to be an even number. And this is where we're again going to use the concept of edges, because remember we had this cycle and it goes from V1 to V2 and then goes from Vp to V1. So now we're going to use the fact that V1 is the element of the odd numbered set. So then Vp has to be an element of the even numbered set. Okay, so now we have the edge, and we're just going to go this onto the new page. So let's just stop this for a second. So now we have Vp V1 is an edge. V1 is the element of that odd numbered set, so Vn. Therefore, Vp is the element of that even numbered set, which has even numbered vertices, and therefore P is even. So we have proven that the cycle is even based on that. Now, just a side note, what is really cool about this proof is that about the theorem as well, is the idea behind if you have A implies B, and you would have seen this in maths, you would have the contrapositive, where not B implies not A. So here we say if we can find a cycle of odd length in our graph, that graph cannot be bipartite. So it's another way to test if a graph is bipartite without actually, going here and drawing it and looking at everything. So if we find a cycle of odd length, then the graph is not bipartite. And this just comes from understanding your math and your truth tables and things like that. So if A implies B, not B implies not A. Okay, so the next theorem we're going to do is pretty cool because it's going to give us a boundary for when we have components in our graph. So the boundary for the degrees, so the maximum degree that a vertex can have in a graph that has two components in it. And to begin with, we're just going to look at the idea of if we have two components of the same order. In other words, we split the graph essentially in two equal vertice numbers. And then what we're going to do is we're going to find the boundary for the degree. So let's actually just do this by an example first, and then we'll say the theorem statement. So let's just have a graph. Let's just write a graph in here. Very simple one. And let's just put in some values or some edges, kind of a situation. Now that is two components, so it's a full graph. All the six nodes on vertices make up the graph, but you can see two distinct components or two disjoint sets essentially. So that is going to be, and here it's again the order of the components are the same, so they both have three vertices in them. So that's component 1, and that is component 2. Now you're going to think back to essentially what was the maximum degree of any simple graph. So the maximum degree of any vertex in any simple graph was n minus 1, right? So if you have your max degree in a simple graph was n minus 1. So now you have a graph which is made up of n, but you've broken it into two. So each of the subgraphs have an order of n over 2. So the maximum degree that any of the vertices in the subgraphs that can have is n over 2 minus 1. And this is what we're going to do as a theorem. So the theorem is, you have a graph of order n, so let G, let's rewrite this, let the order of G equal to n, and let G have two components. Okay, two components of the same order. Okay, so that's basically, again, the situation of then the order for each of those subgraphs or each of those components are going to be n over 2. If x is an element of the vertices set of component 1, then the degree of x has to be less than or equal to n over 2 minus 1. And overall, that makes sense just by if you analyze the example that we looked at there, because the max degree of a graph is usually of a simple graph is n minus 1, right? That means it's connected to all the other vertices in that graph. What you've done here is you have two components, and that means that they're not connected. And if you have these two components of the same order, then if you just look at the one component with its order of n over 2, its maximum degree has to be n over 2 minus 1, just like, you know, when you think about the different ideas with the graphs. So now we are going to have to prove it, and we're going to prove it directly. So you're going to use essentially all this join that we did, but now you're going to write it in mathematical terms to try and actually go through the thought process and tell the reader or the user exactly what is going on and how you can prove it. So the idea behind this was we showed our graphs or our subgraphs basically of the components, and we said, hey, their order is the same. So then I proved that that's essentially where we're going to go. So I've already done the what do we know about it by just doing that join, and now we're going to jump straight into the proving of it. So proof. We showed this, so we need to tell the user it. We know that the vertices of component 1 and the vertices of component 2 are the same. So the number of vertices are the same. And because our original graph was order n, that means our order of our components is n over 2. So therefore, the component 1 is equal to n over 2. Now we need to basically tell the user or the reader, hey, because it's of a component, x can only be connected to the other vertices in that component. And that's an important situation, because then we can immediately jump to that n over 2 minus 1 situation. So as x is an element of the vertices set of component 1, and x can only connect to vertices in its component, therefore the degree of x is less than or equal to n over 2 minus 1. And that is the end of that proof. So sometimes direct proofs can be really quick, and it's the whole idea of just seeing exactly what is going on. Now I have a question for you. If you have a graph of order n and you have more than one component, if x lies in the component with the least order, in other words, it's the one with the smallest number of vertices, then you know that its degree is going to be less than n over 2 minus 1. Why is that? Can you think of reasons for it? So now you have to start thinking of, draw some, like visualize it, like draw some graphs, draw some components of graphs, and see what exactly is going on. So we join to see what exactly is going on. Let's just have a really basic graph situation here. very lazy about it, then we have a graph, and let's just have 3 components. So the graph has order n, which in this case is 1, 2, 3, 4, 5, 6, 12. So V of G is equal to 12. Then we are going to have a situation where we have 3 components. Oh, let's make it slightly more specific because we want to choose in the smallest component. Okay, so now what it's saying is if you have 3 components and you're going to break up everything, in this one here, the one with the least number of vertices, you know that the degrees here are always going to be less than or equal to n over 2 minus 1, even if you don't split them up evenly. Which in our case, it would be equal to your 6 minus your 1, which is equal to 5. So the degree of any of the vertices in that yellow component is going to be less than or equal to 5. And now you need to start thinking about the whole idea behind the components and stuff. So we said if it was 2 components and it was split up completely equally, then the degree of x in either of those components must be less than or equal to n over 2 minus 1. So that it was split up completely evenly. Now we're saying, okay, if we take the component that has the least number of vertices in it, it is always going to be less than or equal to n over 2 minus 1. Now just think about how you'd split it up. So let's just say, for example, just look at another graph and go with, okay, let's split it up so we get 3 equal components, for example. So yeah, we just have another graph, and I'm going to be lazy about it. Let's also do it 12, 1, 2, 3, 4, 5, 12. And let's just do that. Equal components. So the idea with this, every one of these, the order of each one of these components is n divided by 3. And hopefully that will actually explain the whole process to you, because if you look at this in this case, this one's order is n over 3, this one is n over 3, n over 3. Now when you start looking at the maximum order for each of these components, the maximum degree for each of these components, it would be n over 3 minus 1. N over 3 minus 1, n over 3 minus 1. So when you then start looking at and you break up your graph into however many components, 4, 5, 6, 7, etc., you'll notice that if you had to look at the smallest one is always going to be less than the one where they're all equal to, right? Or it's going to be equal to that one. It's not going to get bigger because you take in the smallest component. And if you do that, it will always be less than the n over 2 minus 1. So again, just a reminder, you have a graph, the smallest component will always have the degrees of its vertices less than or equal to n over 2 minus 1. And you can do that by just investigating your graphs and looking at the idea of, look at the case where they're all split evenly. And then look at the maximum degree it will have. Then you think about, okay, even if they're not split evenly, the moment they're not split evenly, you kind of know the smallest one will have a max degree less or equal to the n over 3 minus 1. So no matter, like, the bigger your graph gets, or the bigger the amount of components you get, that smallest component will always have a degree less than or equal to n over 2 minus 1. The biggest component, you don't know that, essentially, or you can work it out, but the idea is just looking at that process, you can work out for the smallest component from there. So you at least have information about the smallest component. Okay, and before we move on, using that same thought process, now figure out what is the maximum degree of a vertex possible, any vertex in your graph, before you know that your graph is for definite connected. So in other words, your entire graph is connected. What is that maximum degree, that situation? And again, you're going to go back to that n over 2 minus 1. You're going to be like, hey, if the orders were equal, then the degree of x is n over 2 minus 1. Now you need to start thinking about, okay, how do I figure out what the maximum degree needs to be in order for our graph to be fully connected? So the components we're looking at, disconnected graphs. Now you need to think about the same process that we used for your if x, the smallest component, is going to be less than or equal to n over 2 minus 1, you're going to utilize that to show what the maximum degree of a vertex is possible before you know the graph is connected. So that boundary situation.